Welcome if you're there, welcome if you're just joining. I hope everyone's having a good weekend. And do feel free to say hi in the chat, and I'll be able to see your comments and questions as we go. So welcome if you're there. Hopefully everyone's well, everyone can hear me. We'll be starting very, very soon. I'm just keeping an eye on the chat to see. Hi, welcome. I can see someone's here already. Lovely to see comments coming in. That's all working well. Brilliant. So I hope we're doing okay. Today we're going to be looking at solving trig equations, which really is one of the big things that's sort of generally quite new when you start doing A-level content. So we're very used to solving quadratics and linear equations, but solving trig equations kind of takes it onto the kind of the next level, really. So let me know if that's something you've done before, and how confident you are with that. We're going to go sort of through all the ideas surrounding it, look at some past paper questions, make a start. So excellent. I'm going to share the screen and we'll be pretty much ready to get started. So hopefully very soon you'll be able to see the slides appearing, and then we'll start working through this together. So we're going to be looking at solving trig equations today. As I said, do feel free to ask questions and sort of share answers in the chat throughout as we go. So let me know if this is something you've done before. Just to get started then, I'm Max. I'm the lead maths teacher at Snap Revise, and I did a maths degree a few years ago, and I've been teaching A-level maths and GCSE maths for about the last 8 years. So there's been some key changes in that time, and it's been really interesting to see how the exams have evolved as well. So yeah, I'm going to look at solving trig equations today, and do let me know if this is a topic you're comfortable with or you've seen before. And as I said, share answers and questions as we go. So welcome if you've just joined as well. Do feel free to say hi in the chat. The main sort of points we're going to look at today are deducing angles at which the trig functions give negative values, solving equations with trig functions in a specified domain, and looking at identities and quadratics to solve slightly harder trig equations as well. We're not going to look at reciprocal trig functions. That's something you sort of generally look at in year 13. I'm not going to do problems involving radians, but it's very much a basis of solving trig equations that I think will be good practice for everyone. So to start with, just reviewing stuff we should know. Depending on whether you've done this before or not, some people solve trig equations using their knowledge of the trig graphs. Others use something called cast diagrams. Either way, we actually really need to be happy with how these functions behave. I'm going to do my best to sketch this as neatly as possible. So the sine graph should look like a wave that oscillates between 1 and -1 and passes through the origin. Are we all quite comfortable with that? I'm just going to sort of look. We should know that the maximums and minimums are 1 and -1. Likewise for cosine, the maximums and minimums are at 1 and -1. But the cosine graph, excellent, is actually just a translation of the sine graph. Brilliant. So if this is actually just a very sort of gentle recap and you recognize all this, that's fantastic. We are going to get straight into sort of solving in a minute. I'm just trying to sketch that nicely. And it would repeat as well. And the tan graph is the sort of slightly bizarre one, because whilst it repeats, it has this sort of strange asymptotic behavior. So you get asymptotes appearing like every 180 degrees. And again, it goes through the origin. So there are like infinite amount of lines that it's approaching but never reaches. And we call those asymptotes. And there's also a couple of trig identities that you should have met or you should meet in year 12. One of which is sine squared theta plus cosine squared theta. I'll just put cos squared theta is always identically equal to 1. Okay, so that's called an identity when it's always true. And the other one, which we hopefully recognize as well, is that tan of an angle is identically equal to sine of that same angle divided by cosine of that same angle. So they are two identities that we're hopefully familiar with. And we're going to bring together all of these skills when solving trig equations. So they're sort of really key ideas we need to be familiar with, but also used to using and applying at different points. So brilliant. Hopefully that's just a very easy review of stuff you should know. Now, whether you're with AQA, OCR, or EdXL, solving trig equations is a really fundamental topic and skill in the A-level maths content. So it's something that grows, it's something that evolves, and it's just something you need to be really confident at doing. In the same way for GCSE, you would need to be really confident with like quadratics. So some people will have done something called a cast diagram. Do let me know in the chat if you've seen that before. But I'm going to sort of talk about how this works, how this behaves, and also I'm going to talk about the graphs as well, and sort of the behaviors and identities that we can work out about the sine, cosine, and tangent functions. So if we look at the xy axis and we look at taking an angle, if this is the sort of 0 line, and we work anti-clockwise, so this would be like 90 degrees, and we work around the unit circle, what we actually find is that the angle that's swept out. Okay, yeah, and I think a lot of people find that they struggle with the cast diagram, especially if it's not a method that schools really go into as much or your teacher doesn't do. But actually in year 13, when you start doing reciprocal trig functions, it's really handy if you do understand it a little bit. Okay, so I'll try and explain it now, but it isn't a method that everyone uses. But we can talk about it as we do some exam paper questions as well. Because a lot of the time you're still going to need your calculator to find what we call the principal value, and then either the graphs or cast diagrams will allow us to navigate to the other values. So basically what we're looking at is that the angle theta, if we start at 0, is the angle that's swept out. Now, if this has a length of 1, it's a unit circle. The y value is basically telling you the sine or cosine or tan value for that thing. So here, if that's theta, and that's the opposite, and the hypotenuse is 1, that's actually going to give you the value of sine. So what we've got is in this quadrant from 0 to 90 degrees, sine, cosine, and tan are all positive. No worries if this is brand new. Some people just work from the graphs. They know that for acute angles, all of the graphs are in the positive above the x-axis, okay? So what we know is if we think of x as the cos value, this is like cos of theta is the x value, and this value here is like the sine value because it's the opposite and the hypotenuse is 1. We can use that to deduce some rules you might know from the graphs as well. So for example, cos of theta, cos of minus theta, for example, is actually equal to cos of theta. Who's seen that before? And you might know that from the graph. You might know, oh, it's just mirrored in the y-axis. But we can also see that on here because, for example, in the negative direction, if this was minus theta, it is actually just the negative version of what's going on up here. Okay, so you can deduce all these other little identities that you could have worked out from the graph as well. And for example, we know these other identities, some people learn these all off by heart. I would say either learn them from the cast diagram or learn them from the graphs themselves. Don't try and commit all of these to memory. But what I'm getting at is there's a lot of symmetries in the sine and cosine graphs. So cos of 180 minus theta, which would actually be over here, if that's theta, that angle would be 180 minus theta. That value is also equal to the negative version of cos theta. And also you could have got that from the graphs here as well. Another identity, for example, some people's textbooks just list these all out. Cos of 360 minus theta is equal to cos theta. So if I show you on the graph, imagine that this is 50 degrees. 310 is 50 degrees back from 360. They would have the same cos value output for y. And some people are used to navigating to it from the graphs, which is fine as well. So in a similar way, if we look at the symmetries and stuff of the sine graph, sine of minus theta is equal to the negative value of sine theta. Has anyone seen that before? And like I said, I never liked learning all of these things as little rules. I liked understanding these from the graph. Yeah, excellent. And it is just to do with the behavior of the wave functions and how they act and how they behave. Now, I know I haven't gone much into the cast diagrams yet, but the key things are we start from 0, and the positive angle we look at is in a clockwise direction. So basically, this quadrant tells you what we're doing for acute angles. If you draw the line in here, it tells you what's going on for obtuse angles, then reflex angles, and then reflex angles between 270 and 360. So it's like working round in 90 degrees. And basically the main thing that the cast diagram tells you is if you're solving, say, a trig equation for sine, we know that sine is positive here and here. So for acute and obtuse angles. And it basically shows you where you would look for your solutions on the graph. Okay, so we'll see that when we maybe do some of these examples. But a lot of people have their own way of just drawing the graph and solving it without using cast. So we'll refer to it, but I do appreciate some people haven't used this before. So let's crack on and start looking at, finding some angles from trig equations. So here we go. So trig functions are what we would call periodic. So what that actually means, in that they're sort of repeating, is that actually because they're periodic, they actually have infinitely many, so infinite solutions. Or in other words, in a given interval. Does everyone recognize that? And we actually have a name for that interval. It's called the domain. So this little bit that they tack on to the end of the questions, this is called the domain. That's basically where we're sort of defining the function from and up to. That's saying like we just care about this little snapshot of the graph from 0 to 360. So we're looking for where the solutions happen. Now I'm going to show you how we would do this on the graph. And if people would like me to, I'm happy to also refer to the cast diagram. But we're solving a trig equation where cos theta is equal to √3/2. Now that's a value some people might actually know. If you know the exact trig values, that is actually quite a special one. That's a very specific one. Now √3/2, if we look up what √3/2 is, as a number, it's smaller than 1. It's actually like 0.866, blah, blah, blah. So √3/2 is like a y value just a bit less than 1. So we know that there's a position on this graph that has that height, and we're trying to find the x value input that gives us that. So in order to find the principal value, does anyone know what we would do? Has anyone got an answer? The answer that basically your calculator will spit out, and effectively for this question, it will be like our first answer. So we call it the principal value, but if you do inverse cosine to both sides of that equation, it will get you theta. And if you do inverse cos of √3/2, does anyone know what the sort of first value would be? So we're going to first of all find the principal value. Superb. Yeah, absolutely right. Thank you for that in the chat. Find the principal value with the calculator. And let's just check everyone is happy with that. And very well done if you got it. Lovely. Yeah, absolutely right. And thank you for sharing as well. That was great that you shared the answer there. So that was theta is equal to inverse cos, just like you would have done with some of these trig GCSE questions. Although for that, we were often solving for the context of like a triangle or something. So that first value is 30 degrees. And that's effectively what we found. Now, like we said, there would be infinite repetitions of this. But what we're trying to do from a graphical standpoint is think where else will there be an input that also spits out 30 as the y value? And we know it's actually going to be somewhere over here. And again, we can use the graph and use the sort of symmetries we know or understand of the shape of the graph. So find other values using the graph. Okay. Now, some people would use a cast diagram, and I'm happy to show you how that would work as well. But basically, remember with these graphs, the key things we need to know is that the key things are happening every 90 degrees. So that's 90, that's 180, that's 270, and that's 360. So for this sort of symmetry to hold true, it's got to kind of be 30 back, like that shape is the same shape as there. It's got to be sort of that same amount back from the peak at 360 as it is from the peak that would occur at 0. So 0 to 30 is the same gap as 360 to something. So this value would be 330. That would be the same sort of distance away from 360. Yeah, absolutely. Likewise, you could think of it as 60 away from 90 and 60 away from 270, which would be 330 as well. So can anyone think how we could check that actually works? Because like any sort of algebra problem, when you're solving an equation, it's really nice if you actually can check your answer is right, so you can move on with confidence. What could you actually do with 330 to verify that it does actually work? It does actually solve this equation. You've got a calculator. What could we do? This was the equation we were trying to solve. Brilliant, absolutely right. If you find cosine of 330, it should hopefully, in fact, be root 3 over 2 as well. And then you know you've got a solution, another solution that works, that the calculator didn't just gift to you at the start. So you've been able to navigate to another solution in the correct domain that does in fact work. Well done. And so then the third and final bit is write down all the solutions. And I will very quickly take this opportunity to quickly explain how the cast diagram would work here, although many people like getting used to one way or maybe used to using the graphs. Now the cast diagram, if we remember, hopefully we can see in this corner, if we do S, A, T, C, now we're dealing with cos of an angle, and it's positive root 3 over 2. So cos is positive here and here. Now you still need your calculator to get you your first angle, which is 30 degrees. Now if you go in the anti-clockwise fashion, it's positive. But remember that this start point is 0 or 360. So if you go back in a clockwise direction, you're going backwards, you're going the reverse way, you're going 30 back from 360. So that tells you that this would be 330. Sorry, that's crammed in the bottom there. I'll basically draw it up a bit bigger, maybe in a spare bit of space in a second. But yeah, basically what the cast diagram does is it shows us the position to look. So there's 30 degrees there, that's acute, but cos is positive here as well. which is 30 degrees back from 360. Because the 0 and 360 line is the same line. So we'll maybe do it in a bit more depth for the next example. But if you are comfortable using the graphs, that's fine as well. Now, sometimes they do get a little bit more challenging because you're solving an equation and it's not just theta. Who's seen this type before? So for this scenario, what you actually need to remember to do is actually adjust sort of the search domain, adjust the domain before you use the inverse function. This is really important. Okay, so I'll show you what I mean. So for this question here, we've got sine of 2 theta plus 25 is 0.2, and we're looking for answers between minus 180 and 180. So actually, if we're going to adjust the domain, this is the first step. Can anyone suggest what it would be? So if theta is between 180 and minus 180, 2 theta, we would have to look between 360 and minus 360. And 2 theta plus 25, we'd have to look between minus 335 and 385. Okay. Now again, the first step, or sorry, the second step, I suppose, would be to, on your calculator, find the principal value. So use your calculator. And if you guys want to do that, you can. Use your calculator to find sine inverse of that value. Arc sine of that value. And let me know if you get a number for that. Because that step is always useful. You're going to need to use the inverse function at some point to come up with some sort of principal value. And let's see what we get. Maybe we'll just do it to like 1 decimal place. It's probably not going to be a nice number, but it should give us that principal value to get us started. Absolutely, it is 11.5. Very well done. And well done if you got that as well. So that's the sort of first value. Now, there are going to be other answers as well, so do make sure we used sine this time, not cosine. And what we've got is we still have quite a lot of work to do, is we actually need to find other values. Okay, so if we're going to do it graphically, other values, I'll show you on the graph, and I'll also show you on the cast diagram. Okay, remember we're looking from minus 335, call it X for now, round to 385. So imagine if this is 180, oh sorry, let's get that right. 90, 180, 270, 360, and we're looking slightly beyond 360. Now, 11.5 is somewhere here, and that spits out 0.2. There's going to be another position here, and there's going to be another position here, and we need to see if that's in this interval. And then there's also going to be more answers here and potentially here, which I think is going to slip out of range. Okay, so the other solutions are going to be 11.5 back from 180. So if I list them off, and they're not necessarily in an order, it's going to be 180 minus 11.5. Does that make sense to everyone? That would correspond to that one, because it's got to be that same gap from the symmetries, yeah? Brilliant. Okay. And also, superb, 11.5 plus 360, which will still actually be in the range we're searching, because we're searching up to 385. And then we've also got 168.5 minus 360. And then if we do 11.5 minus 360, it will in fact fall out of range. So that one's no good. Now this question isn't actually finished. But what I do want to show you though, on a cast diagram, what we would be solving, if I draw it up here, SATC, we're looking for sine being positive 0.2. Sine is positive here and here. So the principal value is 11.5. And it shows us that the next value, would be 180 minus 11.5. So that one would be 168.5. The next value would be 360 plus 11.5, which would be 371.5. And also, if you went in a negative direction from 0, you'd get the first value as minus 180 minus another 11.5. So that would actually be this value here. And that's how you could use the cast diagram to navigate to them. Now, this isn't finished, because what we've actually just found, these values here, is we've found values not for theta, in fact for 2 theta plus 25. Can anyone suggest what we need to do to these answers? Any ideas? Right. Yeah, we need to adjust them. Absolutely right. Very well suggested. So now the sort of next step we need to do is we do absolutely right, need to find the original theta we were looking for using the inverse transformation. Very well done. Of 2 theta plus 25, which is in fact minus 25 and divide by 2. So if we do that for each of our solutions, and you guys might have already done this, so say for example 11.5 minus 25 over 2, we get minus 6.7, which I think someone got earlier, so they were obviously like way ahead of me. But we need to do that for each one. So then you do it with like 168.5 minus 25 divided by 2. I believe we get 71.7, but do check. For the third one, 173.3, and then minus 108.2. Now notice that these answers are all within the original domain we wanted. Okay, remember the original domain, if I tap this back, for theta was between minus 180 and 180. So for theta to be between minus 180 and 180, 2 theta plus 25 needed to be between minus 345 and 385. So we had to find them all and then adjust it. Let's just check, does that make sense? Let's just have a little checkpoint, how we're feeling. And then we'll look at some exam questions of this. See how we go. Brilliant. So actually a really good one to have a look at. Well done. That's brilliant. And thanks for the input there. That was really, really useful. So this one, it's completely like, seems a bit random when we first see it. Brilliant. Thanks, guys. That's great for the feedback. So sketch on a single diagram showing values of x from -180 to 180, the graphs of y equals tan x and y equals 4 cos x. So this is actually understanding and sketching graphs, which you might recognize as a skill kind of from GCSE as well. So if we think about it, the tan graph from -180 to 180, I'm going to start with that. I know that has asymptotes here and here. And remember, guys, with any trig function sketching, you know that significant things are happening every 90 degrees. So let's say that's -90, -180. Okay, so the tan graph looks like that. Everyone was happy with that so far? That's just the first little sort of sketch. And then the 4 cos x graph. Anyone want to suggest how we're going to sketch that? Like basically what has happened to the cos graph? How am I going to sketch 4 cos of x? Because it's asked me to sketch y equals tan x and y equals 4 cos of x. So if I know how cos of x looks, cosine of x, how can I sketch y equals 4 cosine of x, 4 cos of x? How would that look? So I've done this one. I'm going to swap to blue to sketch y equals 4 cos x. What kind of physical graph transformation? Yeah, excellent. Thank you for the answer there. It's 4 times stretched in the y direction. That was really important. It's like the output of the cos graph gets multiplied by 4, thus affecting the y value. Super, brilliant answers. So ordinarily, if we think of those key points on the cos graph, like you guys have both said there, it's 4 times larger for y. So where it's normally peaking at 1 and sort of its lowest point is at -1, that's going to be stretched by 4. Now, because it's only a sketch, the key thing that really affects is, well, the y values, like the scale. So up here where it would normally be 1, it would actually be at 4. And down here it would be at -4. Otherwise, the shape is the same. So if I draw that shape in the cosine graph, which is actually symmetric about the y-axis, it's not really any different to if I just sketch the cos graph, except I'm changing the scale accordingly, but it has allowed me to discover some key things that's going to tie in with this trig equation. First of all, it says the equation has 2 roots in this interval. How do I know from that graph that it's definitely got 2 roots? How do I know that this has 2 solutions in that domain? Remember, when you're solving equations graphically, it's how many times they cross each other. Does that make sense? So this is really interesting because this little skill here, I'm going to show you how to use this graph to kind of solve this problem. But it's a bit of a weird part 2 question here. So the second part says show alpha and beta on your sketch and express beta in terms of alpha. And the roots are alpha and beta where alpha is less than beta. So what this is getting at is these solutions, this value that first solves it is being called alpha. Does everyone get that? So it says this thing has 2 solutions, which we can see the graphs cross each other twice. And it says the solutions are alpha and beta. The roots are called alpha and beta, where alpha is the smaller one. Brilliant. So that must mean that this one here is beta. Okay. And we don't know what those solutions are. It's actually not asking us to find it. It's asking us to relate them to each other. Now, here's a kind of interesting bit. We know some relationships of how these behave. Alpha is literally the distance from 0 to here. Say it was like 70 degrees or something. Now, because of the symmetries of the tan graph, here's a cool little trick. We know that this chunk is actually symmetric to this chunk. So basically, because beta is this value, is everyone happy that we know that in fact alpha plus beta would equal 180? Because this bit is just alpha again. So in other words, when it says express beta in terms of alpha, beta is just 180 minus alpha. Yeah? So it's weird to see because we're trying to like relate them to each other, and as x values, alpha and beta are actually obviously measured from 0 because it's like whatever 70 degrees, 110 degrees or whatever. But also we can relate them to each other using the shape because we know, okay, that bit would be the same. So that plus that we can establish would equal 180. Super, but it's not like that easy to see unless you've done a few questions like this before, which is why I think this was really good to go through. So well done, hopefully that made sense. But again, ties in with understanding the shapes of the graph and how they point to different solutions. Right, let's look at this one. So solve the equation tan x equals -3 in that interval, giving your answer to the nearest degree. So this is sort of a straightforward solving. You can use your calculator, and if it helps, you can use knowledge of the graphs. So I'm actually going to sketch the tan graph from 0 to 360. And if you guys can come up with maybe the principal value, let me know, and then we'll navigate to the other solutions. So that's 90. 180, 270, and then 360. And we'll think about what solutions. Yeah, it's weird, isn't it? It does seem like quite generous, this particular question, and it kind of depends on the board and the paper and sort of how it's pitched, but it won't always be maybe that generous. Let's have a little look. So principal value, if we do tan inverse, let me know what you get. Tan inverse of -3. Be careful. And weirdly, I think the principal value they give you, yeah, is like minus, if we did it to the nearest degree, is like they give you -72, which obviously does work, but isn't in the domain we're looking for. Now, what's cool about the tan graph is it repeats every 180 degrees. So what we can do is just add 180 to that. Or in other words, think it's like 72 back from 180. Okay, so we can find that one. So we're going to get -72, which is kind of out of range. And then the next value and the next value would be 108 and 288. So what's nice about the behavior of the tan graph is you can kind of just keep adding 180 on. So in terms of the cast diagram, what we've just discovered, SATC, is that tan is negative. We know tan is negative here and here, because tan is positive here and here. So we know the angles are going to come out there. Now, the principal value it came out with, if this is 0 or 360, that's 90, that's 180, that's 270. Value the calculator came out with was this one, -72, which is out of the range we're looking for. But if we go in the forwards direction, we're going to hit it here, which is actually 180 on from that line. Okay, so if we add 180, that will give us 108. If we go from 0 even further around, that's like 72 back from 360. So that would be 288. And they would be our solutions. Okay, so let's keep going. This one here, if you guys want to give this a quick go, and then we'll look at rearranging some slightly more involved trig problems. So let's whiz through this. The first thing we're going to do is sort of fix the domain. So this will actually be between 360 and then minus 30. So it's going to be between 330 and minus 30. Okay, and if we do inverse sine, and we need to rearrange this time. So this equation is the same as sine 2 theta minus 30 equals minus 0.6. And if you rearrange that, so we inverse sine it, the principal value we get is going to be okay. Now, what we can do is we can navigate to the others, thinking about the sine graph. So if we think of the sine graph here, we've just been given that value. There's going to be another one here and here. So basically, minus 36.9. So 36.9 on from 180, or 36.9 back from 360. So the values we would get oh no, hang on, sorry. We call this x actually. Would be 216.9 and 323.1. Now they're the values. Now we need to add 30 and divide them both by 2. And I believe that's going to come out as 93.4. Okay. So what we'll do, we're going to look onto like slightly harder trig equations now. So these might involve identities, they might involve a little bit of quadratics, but let's have a little look. I'm going to move this on. So for example, this one here. So for equations involving multiple trig functions, we can basically look to rearrange using trig identities. So those key ones we said about. Okay, now so this one here, can anyone suggest how we could rearrange this so that there's not multiple trig things to solve? Because I think that's what's making it hard. That's what makes this quite nasty. So thinking of those identities, because they both involve sine and cosine, but what could we do to manipulate this question so that we can get started and just solve it? Superb. Yeah, absolutely right. If we divide this through by cosine theta, then we've got 4 sine theta over cosine theta is equal to 3, which becomes tan. Superb. And then you can divide that so you get tan theta, 4 tan theta equals 3. So you're actually solving tan theta equals 3/4. So you've basically just done some rearranging to say, well, this is actually the same, this is encoding the same information. This is really the trig equation we're solving. Really, really well done, well spotted if you got that. Superb. So let's carry on and solve that. Let's get the principal value. and see what comes out and check it's in the actual interval we care about. And I'm going to just sketch actually tan graph. Very good. Well done. Some people have already got principal values. Superb. Thank you very much if you got that. Excellent. Clearly been doing a lot of writing on here. I've just felt the screen really hot. Okay, so we're doing some intense maths here. Right, well done. So it's 36.9 degrees. Superb, those that found that. And that is acceptable. That is in the range. We don't need to manipulate the domain or anything. So that is part of the answer already. So we found there's an answer here that spits out 3/4. I've clearly not drawn this scale, have I? Must look a lot more like that for that to be up at 3/4. But anyway, the first value is 36.9. So we're going to get a repetition of that over here. So we can just do 180 plus that value. Because remember, tan repeats every 180, like repeats every 180. That's the period of it. So the second value would be 180 plus the principal value we found. So 36.9. And I think that's 216.9. So don't forget to list all your solutions that are acceptable in the domain. And of course, as we mentioned earlier, you can check they all work. Sometimes you could have loads of solutions and you can plug them back into this, or if you've got time, you can plug them back into that and check they solve the original scenario, which they should. Superb. So the next type we're going to look at is we are going to look at solving a squared trig function. Basically, by factorizing or using some sort of quadratic technique. By factorizing or using the quadratic formula. Now, there is a web class we've done before, or just using your polynomial solver on the calculator if you've got it. There is a web class we've done about quadratics in disguise and using like a substitution. And that is actually what I'm going to do here. That's what I'm going to suggest here. So I'm going to suggest, why don't we let x equal cosine of theta? Because then this becomes a more obvious quadratic. Okay, the cos theta is the squared term. So this would boil down to 2x squared plus 5x minus 3 equals 0, which is a situation we can deal with a bit more easily. And this does actually factorize into a double bracket. It won't always. This factorizes 2x minus 1, x plus 3. So x is 1/2 or minus 3. So what that means is cosine of theta equals 1/2 or cosine of theta equals minus 3. Now that's a problem. That leads us to a dead end. Cosine of theta can never equal minus 3. If you tried to solve it on your calculator, it would say like math error, calculator error, because it's not possible, because cosine only exists, like fluctuates between 1 and minus 1. So there's a sort of dead end solution set. But this does provide us with solutions. So then from here, we look to solve it in the normal way. So you can find your principal value again on the calculator. And whilst you do that, I'm going to sketch the cosine graph and see if we can spot what the other solution would be. So the principal value that comes out as a half is actually 60. The other value is actually minus 60. Yeah, superb. So the two solutions by the symmetry of that graph is minus 60 and 60. Because remember, well done if you got that. because remember the cosine graph is symmetric in the y-axis, so that's where the other one comes from. Superb. So let me know how you're feeling with that, and then what we'll do, I think we'll finish with an actual exam style question of this type, so that we can be sort of super confident with how this goes. Really good though, that's so good, and thank you so much to everyone who's been sharing answers and comments and questions throughout. So very well done, super. Let's look at this one. So we've got a question here. It says solve 2 sine x squared x equals 1 plus cos x. Now, I used to always get this the wrong way round and think, oh, I want to change that. You actually want to change this because you want it all in the same thing, and we can use the identity that sine squared plus cos squared is 1, so we can change the sine squared term. So what we know is that 2 sine squared can be replaced with 2 times 1 minus cos squared. Does everyone agree with that? We all happy with that? And then we've got to just expand it carefully, pay attention to minus signs as well, rearrange it and deal with the quadratic. Now do feel free to work ahead of me. Sorry, they should have been X's, shouldn't they? Just randomly change the letter. Okay, so getting it all to one side. I'm going to plus it to the other side to make it positive cos squared. Minus the 2 across from the 1, and that would be the equivalent quadratic. And I think this does actually factorize. Okay, so what does that imply about our two solutions? Cos x could be equal to what? Or now both of these are valid. Both of these are valid solutions. So if we think about when does cos x equal half, well, that's going to be x is equal to 60. And unfortunately, in this interval, it won't repeat again. When does cos x equal to minus 1? That would be at 180. And it won't repeat again in that interval. And because it's inclusive of 180, that does count. So they will be our solutions for this question. So that's part I. Is that okay? Hopefully that's clear. Now we'll do another one quickly. We'll have a little look at the following, the second part. So the second part asked us to solve sine 2x equals minus cos 2x. Now this isn't as bad as it looks. This is very similar to what someone suggested earlier, where we rearrange and turn it into tan. So first of all, x is between that and that. So we need to search between 0 and 360. Now, if we know sine of 2x is equal to minus 1 log of cos 2x, I'm going to write it like that, then actually what we know is sine 2x over cos 2x is equal to minus 1. So tan of 2x equals minus 1. So what we can do is we can find the principal value, and then what we can do is half those values. So first of all, let's think about, we're going to look from 0 up to 360. So tan, where is it minus 1? Here and here. So the principal value, if you do it on your calculator, what are we going to get? Minus, oh, actually it gives us this one, doesn't it? minus 45. So if we add 180 onto that, well done. If we add 180 on, I think we're going to get 135. Oh, that's here. And 315. Now what we want to do with those values is half them both. So 2x, no worries, hopefully that's all. Let me know if that's not making sense though, but there's quite a lot going on with this one. Lots of very similar looking numbers as well. So then hopefully we're happy that x is 67.5 and 157.5. Putting it back in the correct range, putting it back in the correct interval or domain, which we can of course check as well. Okay, very good. So I think there's one final little question to look at that would be really good to see. Oh, sorry. Well, here it is. Yes, there is. So this one is already factorized for us, and it said it is given that's the situation. Find the possible values of tan theta. Now, from this bracket, you might think, well, that's really easy. Tan theta equals -1. But do also consider this bracket. We also need to consider when sine squared theta minus 3 cos squared theta equals 0. So I'm going to just run with this. Now that is allowed. Tan squared theta can equal 3. So tan theta, be very careful with this, is actually plus or minus √3. Okay. So actually the possible values of tan theta are are -1, positive √3 or minus √3. So that's your answer to part A. Then it says hence solve. So for part B, we just look at all those different solution sets. Tan inverse of -1 equals -45. And putting it back in the interval, -45 plus 180, theta can be 135. If we consider where tan inverse is √3, we get 60. So that's another answer it can be. And if we consider when tan inverse of minus √3, that would be -60. So if we add 180 to it, another value of theta is 120. So they are actually our 3 answers to this problem. So it sort of stepped us through it because it asked us to solve what tan theta could be. And there are actually 3 values. It could be -1, positive √3 or negative √3. It's very easy to miss that there's two answers to this. If tan squared is 3, yeah, so for tan, you can just keep adding 180. The other two don't behave like that because they're sort of periodic with 360, whereas tan repeats every 180. So if it's ever a question involving tan, brilliant question, you can just add or minus 180 to all the answers to collect more. And that will repeat like that way. And the cast diagram shows you that, but the graphs show you that as well. Absolutely right. Well done. So hopefully after that, we're able to deduce what angles trig functions would be negative from the graphs, solving for a specified domain, and also using identities and quadratics that dress the problem up slightly and allow us to solve harder trig equations. Let me know if you have any questions. I do just want to say thank you very much to everyone who shared answers there. That was really, really good, really useful, and I hope that was helpful. Very well done today. I hope that was useful for you all, and hopefully we'll see you at a session very soon. Well done with that. Thank you for taking part. Thank you for the comments and questions in the chat. Keep well, take care, and hopefully see you at a session soon. Thanks, guys. Well done.